Hi, I'm Dan Poppy, the producer for the Analytics Engineering Podcast. Before we get to this episode, I wanted to invite you to join Tristan May 28th at the 2025 DBT Launch Showcase for the latest features landing in DBT to empower the next era of analytics. Register now at getdbt.com. We'll see you there.
Welcome to the Analytics Engineering Podcast, featuring conversations with practitioners inventing the future of analytics engineering. In this episode, I speak with Lukas Schulte. Lukas is the co-founder of SDF, and he joined DBT Labs earlier this year as a part of our acquisition of the company. I have had the very distinct pleasure of getting to know Lukas over the past year, and I've come to really appreciate him as a human. But that's a story for another day. Today, Lukas and I talk about compilers. SDF is, at its core, a world-class SQL compiler. We talk about the components of a compiler and how they work, different types of compilers and their history, and how one of the most important roles of a compiler is to abstract over underlying infrastructure, whether that's hardware or operating system or browser. We then pivoted to data and how, as usual, the data ecosystem is a couple of decades behind the larger software dev ecosystem. And we ended with a conversation about how the data world could look different with a true multi-dialect SQL compiler and a robust package management ecosystem at its core. Needless to say, this is a world that I am very excited about living in. This was a fantastic conversation, and I think you will enjoy it. Without further ado, let's get into it. Lukas, welcome to the Analytics Engineering Podcast. Before we dive into the main topic of the day, compilers, I want to give you an opportunity to just say hi to the audience and tell everybody a little bit about yourself.
Hi, Tristan. Thanks for having me. I'm excited to be here. I never thought I'd be doing a podcast with you, to be totally honest, but here we are. It's great.
Have you done a podcast before?
I've done a handful, maybe. They're fun. Sometimes you don't really know where the conversation is going to go, and those are the ones where it gets real interesting. I was actually just on one with Anders. Anyways, I'm Lukas. I'm one of the former co-founders of a company called SDF Labs. We're working primarily on compiler technologies for SQL understanding. So specifically, SQL is different across different dialects, across different warehouses, and we wanted to build a unified tool chain for them. Before that, I initially studied electrical and computer engineering and have always been sort of interested in slightly more low-level things and specifically building out tools for other people to use.
What is a low-level tool that you can build in electrical engineering? We've been doing electrical engineering for a long time, are people still innovating on brand new tool sets there?
Yeah, chips are getting smaller every year. There's new sensors that are coming out, and a lot of those sensors are exposed as platforms that other people can build on top of, right? So if you think about like a light sensor or a heart rate sensor, right? Heart rate sensor you can use in a bunch of different ways, or step counting you can use in a bunch of different ways, and all those are.
Did you work in that world in sensors?
That was my sort of initial introduction to data. Actually, was sensors and the logs that those things were throwing off.
That's very cool. So you alluded to this in your intro. You joined DBT Labs as a part of an acquisition of your company. And by the way, you're never a former co-founder. You're always a co-founder because it's just a thing that you did. No one can fire you from having co-founded a company. I think that it's fair to say that the core way that you think about the technology that you and your team built at SDF is a multi-dialect SQL compiler. I want to get back to the SQL part of that in a little bit, but maybe we can start more broad-based in just the compiler part of that. My guess is that basically everybody listening to this is going to be familiar with the term compiler and is going to, on some level, have a conceptual understanding of what a compiler does. You write code, much of the code that we write is compiled into something that machines can understand. Fine. But you maybe can help us dive into this topic at a little more depth. How would you define a compiler?
Yeah, I mean, I think the one sentence is essentially what you said, right? It's something that takes higher level human readable code and translates, compiles, rewrites, code generates lower level machine code that is much harder for humans to understand and much easier for machines to understand. Compilers typically have phases. This isn't like a one-shot process. They have a front end that deals with like the language that you're working with, and then some middle component, right? Usually that's called an IR, right? An intermediate representation, and then they have a backend, and the backend takes that intermediate representation and then actually compiles and optimizes and generates the actual machine code that machines use. So compiler is it's a single word for like a very very complex process that happens all around us, right? It's like how computing works. It's amazing.
I want to go deeper into the different phases and how all of it works. But in preparation for this, because I'm not a compiler historian, I was asking O3. I just got access to O3. I don't know if you played around with it yet. I found my experience so far to be a little bumpy. I think they're still refining. But I was asking it, who built the first compiler? Do you know?
I actually don't know. I know Fortran is like the first, like people like Fortran as kind of the first real compiled language, but I'm curious who built the first compiler.
So apparently, and this is like a language that I think none of us have really ever heard of, but it was Grace Hopper.
No way.
It started being used in 1952.
Cool.
Like, yeah, kind of neat.
That's amazing.
So we've been building compilers for a long freaking time. What are these common elements that essentially all compilers you would expect to have? You talked about the front end and the back end. There's intermediate representations. How does it all come together?
There's a lot of different ways that this comes together, quite frankly, right? There's like
Oh, is that true? Or like, there's no like single standard way that all compilers work?
it is standard like structurally, but exactly what happens, right? So even for example, there are interpreted languages like Python, and there's compiled languages, but somehow there's still a compiler that like takes Python code and makes sure that it can actually run on your machine, right?
So is that fair to say that like even if it is not called a compiled language, like Python is an interpreted language, like you say, there still is a thing in the flow of like executing Python code that one could refer to as a compiler,
Yes, it's just called a JIT compiler, a just-in-time compiler, because
just in
it
time.
does things like line by line, essentially. And it's really great for debugging, right? Like writing Python code, it's very clear to see exactly where things are because hey, we don't have to compile the entire project. You kind of get to step through line by line and follow along with what the compiler is doing. So yeah, although structurally things are similar, but practically like under the hood, what's happening is different. I think the closest that you can get to something that is more universal is something like LLVM, where there's sort of an intermediate representation in the backend, a set of tools, tool chain that is common. But yeah, there's a lot of different ways for accomplishing the same thing.
Okay. At the front end, there's some ability to kind of rip apart the like text that a programmer has written and to turn that into symbols. Is that the right way to refer to that?
Yeah, absolutely. There's a preprocessor, and the preprocessor starts by work at DVT. DVT deals a lot with macros. Preprocessor, for example, will expand macros in a compiler, and it'll get rid of comments and other things that are not necessary for the machine to be able to understand. And then there is a lexer and often a grammar that defines what the language should be. And then you get a symbolic representation, essentially tokens that you can work with. So yeah, absolutely. You start getting a lot of symbols, and then you package those symbols into a tree and then you're able to start, doing syntax validation and semantic analysis and so on and so forth.
You're using a lot of big words, syntax validation and semantic understanding, and all of that. I can totally imagine this kind of rough first stage where I ship my 100 lines of Python to a just-in-time compiler, and its first job is to just like understand the things that I have written and map those to like concepts that it knows about. At some point, it needs to reach a level of certainty about what you are trying to express such that it can actually start to point to memory locations and perform mathematical operations and all of that. How do we proceed through those kind of subsequent stages?
Yeah, so this is now we're starting to get to the middle of the compiler. Maybe to sort of break down the before I get to the middle, maybe to break down some of the bigger words, like the difference between syntax and semantics.
Mm.
They kind of feel like the same thing, but maybe the simplest way to think about it is, let's say you have a Python program, right? And you have whatever x equals x plus one. You can write that has like a syntax, right? That is a correct Python program, and then there's semantics, right? There's a meaning that, hey, we're increasing x by one. But you could also write that as x plus equals one. Different syntax, but same semantics, because the result is still going to be x incremented by one. So this is kind of how to think about syntax versus semantics, where syntax define, hey, what is a correct, an allowed way to represent something, and semantics are, hey, what does that actually mean? So semantics of x equals x
What
plus
is the
one.
idea that you're expressing?
Yes, exactly. Yeah, that little analogy always helped me when I was learning about this stuff. Yeah, syntax and semantics. Once we have semantic representation of our program in SQL end, this is our logical plan, right? It's a logical representation of the algebra that we would like to do on some data. You head to the middle of the compiler, right? So going from a logical plan in SQL land to a physical plan, right? The physical representation of, hey, how many cores and how much memory and how are we going to load exactly what Parquet files or CSV files. That middle part can then do a whole bunch more optimization and additional analysis and validation. And sometimes I think in databases, right, we might have a better understanding of like the bytes scanned, for example, right? You have to have a perfect understanding of the program, and you have to have a perfect understanding of the data that we're accessing to have a good understanding of, hey, how many bytes are we going to be working with. And then once you have that sort of transition from logical to physical plan, right, that you also start doing machine level like optimizations, where, hey, maybe we are on an Intel machine and we have exactly this instruction set, or we're on an ARM machine and we have that other instruction set. And in modern tool chains, at least for things like Rust and C++, you have LLVM, which is this compiler tool chain that helps to go from this unified intermediate representation to many different backends, right? So many different target um, operating systems, CPU architectures, etc.
This is very interesting to me because it gets into the history of all of it. If you go back in time, not 75 years to Grace Hopper, but if you go back in time, I don't know, to the 70s and 80s, you're like fully in the mainframe era. And my understanding, and certainly I was not a practicing professional during this period, but my understanding is that in the mainframe era, the dominant characteristic of the software ecosystem was that all software was built to run on a particular type of mainframe. Essentially, like all the programs were compiled and really could only be run on that computing architecture. You couldn't have a universal binary that runs on Mac OS and also on Windows and also on Linux. You mentioned LLVM. Have we been like working on abstraction layers for like multiple decades to provide this kind of like cross chipset portability?
I also was not a practicing professional in the,
Right. Yeah.
the mainframe era, but yeah, from my understanding, software, like the software ecosystem, is built on abstractions and increasingly higher levels of abstractions, right? Even you used to have to care about garbage collection and like whether you're accessing
Yeah.
the right bytes of
That's
memory.
like a huge efficiency gain in the history of languages, right?
Exactly. It's very analogous to what is, I think, happened with compilers as well, where we talked about these three big phases: front end, middle, and back end. But within those, by creating sort of unified intermediate representations, you have a unified framework that you can build the back end off of to make sure, hey, we can compile this for a MacBook ARM chip and a MacBook Intel chip. And that, I think, is just years and years and years of work to make sure that you get the right intermediate representation that has the right level of flexibility and depth to be able to express everything that you want to express in C or C++ or Swift, in this intermediate representation, and can be compiled to many different architectures. So yeah, layers of abstraction. It's a beautiful thing.
I get really curious about like who has spent all the time to build all those layers of abstraction? Because, and I don't want to fully get to here because I want to get here later, but similar layers of abstraction have not taken place or have not been created in the data ecosystem, I think, to
Correct.
as much of an extent. But like, who is it? An academic community? Is it an open source community? Like, who builds compiler technologies such that they have incentives to provide these layers of abstraction?
I think the tech giants have invested a huge amount, and then various academic institutions as well. LLVM was super heavily invested in at Apple, in part, because they started working on chipsets quite early, right? They started working on mobile chipsets.
Hmm. That's so interesting that Apple would do that because one of their big problems 20 years ago was that they had their own chips and
Yes.
nobody compiled stuff for their chips. So you can totally imagine why they would have an incentive to create this like cross compatibility.
Yeah, and they tried it a second time and they did much better. And I think in large part due to the ability of compile like the advancements of compiler technology, right? Allows you to create an application that runs exactly the same on an Intel MacBook or an ARM MacBook with relatively little effort. And that used to be complete rewrite, right?
So you folks have been working in Rust with SDF for a long time. And what percentage of your time investment goes into making sure that you can ship Rust binaries on both Windows and Mac?
I've never thought about that question.
It's like negligible, right?
It's less than you would think. Yeah, it's what it really what it does. Any compiled language requires you to set up infrastructure, right, for all the target architectures that you want to hit. Um, but once the infrastructure is there, right, we just make sure that the same tests run on Windows, that run on Linux, that run on Mac. We test different architectures, but once the test infrastructure is set up, the tool chain is there to be able to automatically compile, test, validate, etc. So our infrastructure looks almost identical on Windows as it does on Mac, as it does on Linux. And once that tool chain has been built up, using it costs only some GitHub Actions minutes.
Yeah, CI minutes. Yeah, that's pretty neat. But you folks, you built the tool chain. You didn't have to like rewrite the application. You didn't have to build really any kind of foundational technology. You're like using stuff that exists
Yes,
to make that happen.
absolutely. And again, like LLVM sits under the hood of that.
We've mentioned LLVM several times. Can you just define what that is? When did it become a thing?
Yeah, it's LLVM's been evolving for the last 15 years or so. It is it's not a compiler per se. It is a tool chain for compiler development that provides a unified or a series of unified intermediate representations, and then the backend to compile to target dialects. So what that means for for development in Rust, for example, I can say, hey, here's my Rust code. Um, Let us add a target, and then the Rust compiler creates an intermediate representation, and that intermediate representation is then turned into machine code for the target CPU and operating system microarchitecture that you have selected. And that flexibility means that we can, write code once, but build it for many different platforms simultaneously.
Are there trade-offs involved in LLVM? Like you got a bunch of portability, but
Yeah,
your compiler is slower, or I don't know.
it used to
Is
be.
it just like everybody now just does it this way?
It used to be slower, yeah. I think GCC for quite a while was faster, but I believe that in the last like 5, 6 ish years, I don't even think there's a significant performance penalty.
So there's been real consolidation around the LVM architecture. That's interesting. Okay, I perceive this as a weird thing about the compiler world. Maybe people who live in it just kind of accept this as normal, but I find the act of bootstrapping to be such a weird thing. So compilers are one of these things that like are infinitely self-recursive because in order to build a compiler, you have to write programming code and then well what are you going to use to interpret that programming code? Well, like a compiler. And so there's this weird, almost like mitochondrial DNA type of thing where like all compilers can be traced back to the original compiler because they've all been used to build each other. Can you explain like what does it mean to bootstrap and how does that process work?
This kind of goes back to your more levels of abstraction, right? Like it is ultimately just adding new levels of abstraction. So I can't remember if it was written in C or C++, but the original Rust compiler was not written in Rust, obviously, right? Because Rust didn't exist yet.
Right. It didn't exist.
So then, Rust became better. And then the maintainers of the Rust ecosystem decided to rebuild the Rust compiler in Rust. So now Rust is compiled in Rust and written in Rust, and is the result is the language Rust and the toolchain for Rust that lets you build Rust if you want to. So you are correct. It is now fully self-contained and like kind of infinitely recursive in a funny way.
I think that plays out with like basically every language because you clearly have to like get there from somewhere. So you have to choose another language, but then you probably don't want two different language skill sets in your community. Like one skill set in C++ that built the compiler in the first place, and then another skill set in Rust where people are actually building programs. You like want everybody to work in the same ecosystem.
Yeah.
It's a weird dynamic. Is that saying that one day we will move from Rust into SQL, and SQL will just be no. I
The whole
think
world
that's
is going to be everything is going to be SQL.
everything's going to be SQL. I think that might not be a great idea. Okay, we talked about Python a little bit and how it's interpreted and there's a just-in-time compiler. There's a couple of other ones. We talked about C++ and Rust. Those are kind of more pure compiled languages. What about Java? What about TypeScript?
Java is compiled, but there's a automatic, like a garbage collection mechanism. So it feels like a slightly higher level compiled language than something like C or C++. And then TypeScript is it's actually interesting. Like TypeScript is a little bit more analogous to DBT and DBT SQL, in that they're the intermediate representation, right, that you compile down to
Is another language, right?
is actually just JavaScript, exactly, and then you interpret JavaScript. So this was I think, incredibly clever design choice because it meant that you have compatibility between TypeScript and anything that runs JavaScript. In the same way that I think it was incredibly clever of DBT to start with, and the intermediate representation being just SQL, right? Even though DBT has all these other syntax and macro capabilities, but that means that DBT can run anywhere that SQL can run. And I think this helped TypeScript get a lot of adoption very quickly.
So you can't take TypeScript and like create a binary out of that. That's just like not how TypeScript is built to work.
No, you can package it up in you could package it up in another thing that contains an interpreter, but you still need the JavaScript interpreter.
Interesting. Okay. You made a statement to me one time that I thought it was a throwaway for you, but it really has stuck with me. You said something like compilers are the foundation for every software ecosystem. Can you explain what that means? Like in what ways does a compiler enable a software ecosystem to either thrive or not thrive?
How much time do we have? That's a big question. Yeah, I think that there are two really big drivers in software, in my opinion. One is abstractions, which we've talked about a little bit already, and the other one is standards. Right, you want to have like one way to interface with a USB device, not 10 different ones, and the same goes for software. Right, you want to have one clearly defined way to express a TypeScript application, not multiple. Same goes for Python. Same goes for C. So there's ANSI, there's standards bodies, but they can only do so much. So very frequently, what you have is a sort of canonical compiler that is broadly accepted and compatible with some very base level, like bare metal CPU architecture, right? So you can take Python. It doesn't matter if you go to Azure. It doesn't matter if you go to a Raspberry Pi. It doesn't matter if you go to like a Mac ARM machine. You can run the same Python code and get pretty much the same results guaranteed. And that is incredibly powerful because it enables portability of code, and it also enables portability of like mind share, right? People can move to different companies and take their learnings and add new contributions in different places and potentially reuse contributions from other places with a certain certainty that those things are going to work.
So it's kind of funny that I'm very novice when it comes to my software engineering skill set, but I like literally never think about, will my Python output the same results in AWS and Azure and on my local machine and wherever else. But that doesn't happen automatically. That happens because there is a standardization effect that comes from compilers. Is that what you're saying?
Yes, exactly. Like imagine there's so many libraries and package managers. You want those packages and libraries to behave the same, no matter who's installing it, at what point in time, and on what machine. And the compiler is kind of the very base primitive that enables that sort of consistency.
Are there language ecosystems that do a better and worse job at this? You're smiling right now. Are you worried about inciting a flame war?
Yeah, maybe. No, SQL does a particularly bad job at this. If which is maybe how we got started at SDF in the first place. But yeah, SQL does a particularly poor job, right? Because as anybody that's worked at more than one company that uses SQL knows, you can't take a SQL statement and guarantee that there's portability from one data warehouse to another. You might get different results, even for like very basic things like what identifiers look like and so on and so forth.
Leaving SQL aside for 1 second, and then we'll get right back to there. So software engineers tend to adopt programming languages because they have neat features or because they have really mature compiler and package management and these types of, like, could you make a statement that the like package management and compiler ecosystem inside of Rust is like in some way differentiating or more mature?
Absolutely. People make those are, I think, convenience based decisions. And that is great. Like I do that all the time, right? Where, hey, I want to build, a database application. It turns out that Java has been sort of the root of so many data tools for a long time that you have all the connectors, you have the right libraries, you have authentication methods, you have sort of other compute primitives. So hey, Java feels like a really great place to start if you want to take advantage of a rich sort of ecosystem of tools and libraries that you can build on top of. But there are other sort of trends taking place that influence what is really not just state of the art in terms of capability, but state of the art in terms of usability. Um, 20 years ago, I think we were at like Core 2 Duo, right? Like it was a novelty to have two processing cores on a machine. Now, this MacBook has 12 cores or 14 cores or something like that, right? So, hey, now you actually need a different sort of programming paradigm and potentially a different programming language, different compiler technology to be able to take advantage of the fact that we now are now deeply in the world of many core architectures. And it turns out that C is much more annoying to write to write the, multi-threaded things in than Rust. Rust makes that stuff super simple, and a lot of it has to do with the compiler and the language features that are available. So we're going to pick that because of the forward-looking and current sort of world state that we're in. Whereas 20 years ago, maybe would have picked a different language.
Yeah. Okay. It's interesting that and seems like would kind of be obviously true that the changes in the technology ecosystem necessitate like changes in developer tooling. So let's like finally make our way around to data. You started us off by saying that SQL is not standardized. I think that that's obviously true for anybody who is listening to this podcast. We've all kind of had to work with different dialects and dealt with non-compatibility and all of this stuff. And that's honestly, sometimes I feel like, what's it called when the person who has been kidnapped develops sympathetic feelings for their kidnapper? Is it Stockholm syndrome? Yeah, right. I feel like all of us in the data industry have like Stockholm syndrome for the databases because we like forget that everybody else, software engineers, like live in a world of portability and have for a while. So this is the world today. And it does seem a little bit analogous to what you were talking about before with the like multi backends, like the multi like different chip architectures, but we're kind of missing our LLVM. Is that a fair comparison?
I think that's a very fair comparison.
Why is this the way that the world is in data? Is there like an inevitability to like SQL dialects being different from one another, or can that change?
It is already starting to change, right? There are certain like commoditization trends that are happening, right, where people are sort of agreeing on more unified architectures, um, or consolidation trends, like that consolidation creates commodities. Um, so Iceberg, I think, is like a very clear and very public one, right? Where hey, it wasn't, one of the things that was proprietary for a long time was how we deal with storage. Turns out, hey, if we create a unified standard for how we deal with storage, metadata, versioning, etc., a lot of companies could benefit, and many databases could plug into that storage mechanism. Now, for SQL, we haven't seen the same technology be developed just yet. Um, there are really interesting tool chains out there that are moving in this direction. Substrate is one, right? The goal there for Substrate was to create a unified intermediate representation of what a logical plan looks like. There is Data Fusion, which is looking to sort of standardize what the compute backend looks like and make trying to make functions more pluggable. So the technology trends are starting to appear, but it does seem like we're, at least in SQL land, still, 10, 15-ish years behind where the software ecosystem is at the moment.
So if we're 10, 15 years behind, okay, we're like trying to get ourselves out of the Stockholm syndrome situation where we kind of accept that this is the way that the world is, and we're not even like trying. The data ecosystem isn't like clamoring for standardization at this level for like a common representation where that can kind of be compiled down to all of the different targets. Can you convince me that this is possible? The promise of SDF, if I can speak for you, and please tell me if I get this wrong, is that you should be able to write a piece of SQL and transparently to you, that piece of SQL should be able to run on any of the underlying dialects or engines that SDF supports. And today that's a handful, and in the future it will be many more. And that doesn't require that capability of running that same piece of SQL on multiple different platforms does not require intervention by a user. And it's not probabilistic. It doesn't mostly work. It like always works. Is that a fair way to summarize with the kind of core technical benefit that you think?
Yes, I think you summarized the user benefit. Taking this back to compilers, the goal, maybe very similar to LLVM, is to create a unified intermediate representation that is the same across all dialects. And then, given that unified representation, then you can decide what you want to do with that representation. Maybe you want to, translate from one dialect to another. Maybe you want to analyze that logical plan for um, data governance reasons, but the target for the technology is this unified intermediate representation.
And then you can do with it what you want.
Exactly.
If this has worked in the land of maybe honestly the most directly analogous thing is not LLVM. Maybe it's like you were saying before, it's like TypeScript and JavaScript. This is an era of computing that I actually was like very active in, but like the early days of building web applications, you almost like just didn't want to use JavaScript at all. You just did everything on the server side because, pardon my language, JavaScript compatibility across multiple browsers was a goddamn nightmare.
That's true.
And nobody even thought that like of course that's true. Like it's not even clear that we should be trying to fix that problem. Like let's just shove all the logic into the server and just like do minimal JavaScript when required. But we have gotten to a world where you can pretty reliably write front end code. I don't know about pretty reliably, like maybe completely reliably. Yeah, write front end code, and it just like you don't care what the target browser is at all, right?
Yeah, no, this is totally true, and I think, to your point about we're not going to wait for JavaScript to get better. We're just going to render everything on the server. If you think about the time horizons there, right, you're probably thinking it in the terms of like, hey, let's get a feature out in the next 3 months, or then in the next 6 months or a year. Compiler development does have a longer horizon for improvement, but there are such ecosystem knock-on effects, the even relatively small changes there result in huge usability improvements long term. So what can I do to convince you that we can get there in SQL? I the maybe best thing I could say is look at historically those improvements, right? For how much JavaScript development has improved across browsers over the last years, or how easy it is, for us at SDF at this point to write some Rust code and have it be executable with exactly the same behavior on so many different architectures. Um, there's proof that these increased levels of abstraction will keep happening as long as there are drivers in the ecosystem and really material user benefits. I think we have those in SQL, and I think we're at that point in SQL where that investment really, really makes sense. And yeah, that's why we were super excited to start SDF. And that's why I'm excited to sort of continue the journey here at TBT.
It's almost crazy to imagine that we couldn't accomplish this, because in order to believe that we couldn't do it, you would have to believe that SQL, and it's anybody who is listening to this, if you ever get a chance to meet Lukas in person at a conference or something like that, just like start asking him about the like weird inconsistencies between SQL dialects, and like they're very real, and they are numerous, but they are not even close to as widely divergent as the Win32 API versus the Mac, whatever they call the underlying programming API is. Like we have developed reliable abstractions in the past, and they work, and we rely on them to run like literally the infrastructure of the world's compute fleet. And I think we can do it again with SQL.
I think so too.
What does the world look like in data in a world where you've got an abstraction layer like this? How does it impact the way we build data systems, the way that practitioners work on a day-to-day basis?
Blue skies and sunshine. No, I think I, one very material improvement that I think maybe even DBT can play a role in driving is more formation of libraries and other higher level abstractions. Remember, I said there's
Yeah.
two things, right? It's just like compilers and abstractions. Abstractions you get through libraries. SQL has no very good abstraction model. There's no import statement for SQL, and being able um, to create those libraries, kind of want two things. One is you want the ability to run code across platforms, right? Because otherwise you have to create, multiple different package managers depending on which data warehouse you're using. And B, you need a community that's large enough to actually start investing in those libraries. And if every SQL writer on the planet is sort of siloed into their, pick your fighter team of data warehouse, that ecosystem is much smaller and much more fragmented. So I think there is a chance for this to have this very unifying effect and create a big driver and opportunity for libraries and packages to evolve in the ecosystem.
I have talked about this publicly before, but it doesn't come up that often. The original thread that I was pulling on with DBT was package management. It was a way to figure out how to deploy standardized code alongside of standardized data ingestion pipelines into users' warehouse. And in the early days of what was then Fishtown Analytics, we spent a lot of time building packages, and the DBT package management ecosystem like works better than not having one, which is the world without it. But gosh, there are so many things that you run into when you try to build analytical packages, and the first irritating one is just nobody wants to spend their time building a package that can be used by multiple people, and then realize like actually it's really only useful for the people that use the database that you're using, as it like cuts down the utility immediately. And I remember back in the day using some kind of very unsophisticated methods to kind of provide some cross database compatibility, but it's like an uphill climb, which makes you just want to go back to your own corner and say like, never mind, I'm not going to generalize this.
Yeah, that's true. And I think DBT's success in part, it is incredible to see how much traction adoption there is for code reuse. Given even this small semblance of a package manager, right? Where hey, we're going to provide a little bit of imperative capabilities to SQL through Jinja, right? You can write for loops and things, and we're going to create a package management system so that you can import a package and at least for the major ones know that it's going to run the same whether you're on Snowflake or Redshift. how powerful has that already been, right? It's been incredible to see the adoption of that. And I think that is such a great thread to keep pulling on, because SQL is still a very, very widely written language. Like it is up there in the top 3, 4, 5 languages in terms of actual use, all without having this sort of ecosystem or great amount of consolidation behind it.
Yeah. It is very hard to predict exactly how a software ecosystem will evolve, but it has been like very consistently true over time that if you give engineers the right abstractions and the right kind of foundational tooling to create reliability across platforms, then novel, interesting things will happen. And so I almost look at the technology that your team has worked on, and it is now becoming a part of the DBT platform, as this like fascinating event horizon. It's like very challenging to see beyond it, but I guarantee you that I will want to go back to building more DBT packages in a world where I can just like reliably ensure that they work across every database platform.
Me too.
Lucas, thank you so much. We could have done a full 4-hour episode here. We've tried to cram a lot into a little bit of time. Maybe we'll have to get you back on here after we've seen some of the fascinating things that folks are building. But thank you for hanging out and for educating us.
Thanks for having me.
The Analytics Engineering Podcast is sponsored by DBT Labs. I'm your host, Tristan Handy. Email us at podcast@dbtlabs.com with comments and guest suggestions. Our producers are Jeff Fox and Dan Poppy. If you enjoyed the show, drop us a review or share with a friend. Thanks for listening.